I am part of a group that's called the Neuroinformatics Research Group. That is a group now of about 30 people that we manage. We do data management for radiology research. So we have research projects that have a lot more people involved, but we do the compute side of things. So we manage the computers and everything else. I focus on a virtual infrastructure and storage infrastructure and automation of those environments. We have a virtual infrastructure of about 300 virtual machines and about 10 petabytes of physical storage. As far as BGFS goes, we have 2 BGFS projects in my environment. On campus, I'm not aware that others are using it, but there's a lot of different independent groups on the WashU campus, so I can't say for sure. They vary in size tremendously, but what they do have in common is we utilize WashU's clinical medical images, which there's over 2 petabytes of medical images in their, what they call a PACS storage system. And those consist of MRI images, CT scans, PET images, mammographies, and so forth. But it obviously adds up to a lot of image data, and most of it boils down to JPEGs underneath. The first BGFS project that we brought on board was with a collaboration with a group called White Rabbit AI in San Mateo, California. They're a venture capital funding company, and they are using the breast cancer images that WashU owns, that we spent close to a year meticulously scrubbing of PHIs just so they could have access to this. They built a cluster of 8 processing nodes with 9 GPUs per node. It's all interconnected with 100 gigabit InfiniBand, and it's supported with 4 BGFS nodes that are pure SSD storage. I'll go into the details of that shortly. The other project is a project called Mirror, where we are going to expose all 2 petabytes of clinical data to researchers at WashU and abroad. Part of the problem with using clinical data for research is, in order to legally use it, you have to remove all the personal identifying information in it. And that is very challenging when you're dealing with these large data sets, and can take a huge amount of time. And like I said, we spent close to a year scrubbing the 200,000 breast cancer images. And that's just a very tiny fraction of all the medical imaging data we have. So we're building the new process to where we have container-based processing, that we audit the containers before we allow processing, but the containers can access the PHI included medical imaging data for processing, as long as the output can no longer have PHI in it. So essentially, the researchers will never come in contact with the PHI with this firewall we're building around it. It's currently in the prototyping stage. We expect to be in a semi-production stage by later in this calendar year, and full production in about a year from that, where we can have people bringing in their own containers for research with our data sets. Some notable things that we've done with both of these clusters is all the BGFS servers are PXE booted, so they have no local storage for the operating system. This gave me a couple major advantages as I was working on building these systems and allowing us to do experimental things. The root file system on the PXE server for these BGFS servers is ZFS. That allows me to do rapid cloning and snapshotting of the root file system. So, for example, if I want to do an upgrade to BGFS, it can be run across the entire cluster. If something didn't go right, it's as simple as just doing a ZFS rollback and rebooting. Since we kind of consider all this a little bit experimental, that's been grateful and that we don't have to worry about creating a big downtime with an upgrade. We always know we have that quick fallback to go on. The system is also Puppet managed, as most of our compute research infrastructure is. The White Rabbit AI cluster, like I said, is a 4-node cluster. It has only about 30 terabytes of data on it, with the 200,000 mammographies on it. This system was built specifically for this purpose, and it won't grow beyond that. And it was also built as an experiment to understand BGFS itself for our greater usage. Like I said, this is a collaboration with this group. My background building a lot of storage systems, I was able to come up just from my gut knowledge about building storage systems, about how much CPU, how much RAM, and so forth can build these systems. So this system was actually built from parts, but server grade Supermicro parts. It is an AMD class server, and the number one reason for going with AMD was not price. It had to do with PCIe lanes. The AMD single socket CPUs have 128 PCIe lanes available to them, whereas the single socket Intel ones have only a fraction of it. I think it was 40. And with only 40 lanes, you're not going to move a huge amount of data when you start connecting lots of HBAs, InfiniBand, et cetera, to it. It's just, you're going to become bottlenecked right there. These AMD chips have lots of lanes available, and that seemed like a clear-cut choice for building these systems with it. The other reason for going with the single socket was so that you get rid of the QPI potential bottleneck between two CPUs in a system. Since there's plenty of PCIe lanes on a single AMD socket, this looked like a good contender to build out what we needed. Since, like I said, this was built on kind of a hunch of what I suspected it was going to take to do the output. The goal here was to get 100 gigabit per second output, saturate the InfiniBand on this network. We didn't quite achieve that. We got to 27 gigabytes per second across the 4 nodes. We are seeing close to that in the production environment now. We were hoping to hit close to 40 gigabytes per second. Not quite there. We'd probably take another node just like this to get there. The current build is, like I said, is going to be for the entire clinical data set that WashU has. The goals for that system is going to be to store all 2+ petabytes of data. We want it to be ZFS-based storage. Number one reason for that is bit rot protection. If you're using RAID controllers, you're guaranteed you're going to see dirty data returned to your clients with no indication that data is dirty. It just simply happens. If you run ZFS long enough, you will see the number of times that it catches bad data returned from disks that RAID controllers just simply pass on down the line, and you're dealing with maybe 1 bit flop in a JPEG. But if you're dealing with a JPEG, 1 bit flop makes that a really bad JPEG. And if you're trying to do AI training on it, if you got 1,000 images and one of them has got a bit flop in it of a JPEG, you can really mess up your training. So it's not a worthwhile risk for us to run RAID controllers, which would be more performant than a ZFS backend, but having the risk of bit flops in it is not one we want to take. The ultimate build should have 50 gigabytes per second sustained throughput, and we want to build it on a grant-funded research budget. When you buy from storage vendors, yes, they provide a lot of value, but you got to pay for that value. So we're trying to build that value in-house, and that's why I'm busily trying to learn these clustered storage systems and how to build them to be the most efficient we can. Currently, the prototype system is built on old hardware, most of which we had around. The only hardware that was not old, but we could spare a couple servers of, is the 2 metadata nodes. They are 2 6-core. They each have a 6-core Intel processor at a decent clock rate, a single NVMe M2 socket Samsung 870 Pro SSD. The storage nodes are old Dell 610s. We've got two sockets, 6 cores apiece. They have 96 gigs of RAM apiece in each of these hosts, and we've connected 72 10,000 RPM 900 gig hard disks that were recently retired from another storage system. Old 9201 SAS HBAs. All of our systems are running CentOS 7. We are experimenting with different kernels. Currently, you see we got the metadata nodes on a 4.4 kernel and the storage nodes on a 5.4 kernel. I was trying to use the 5.4 kernel on all the systems. However, we wanted to run a BGFS client also on the metadata nodes and didn't have compatibility there, so it has the 4.4. Some interesting data came out from this prototype node. I used almost all of the performance tuning that was presented in the last BGFS community meeting, and was seeing really poor overall read performances until I turned primary cache to all. I had previously seen recommendations to set the primary cache to be metadata only on the data nodes. However, the read performance was consistently poor across all 5 nodes, of only getting about 1 1/3 gigabytes per second across 5 nodes. As soon as I turned that to all, I was consistently getting 10 to 11 gigabytes per second. I think that might have to do with newer versions of ZFS. I'm running version 0.8.2, and there's been noticeable performance changes that have happened between the ZFS versions. 7 was much slower than 6. 8's definitely much faster than 7 and 6. Sorry. Currently, these were all TCP connected, and we were running into performance problems. I'm working on adding InfiniBand to that now. InfiniBand is always a challenge. I'm getting there. That's what I have for you today. Any questions I should be aware of here?